Thank you very much for the invitation, Stefano, and the other organizer. So this is the title of my talk, and it will be very short, and I will briefly speak about a few contributions which are there. So let me tell you that today I will be focused on the deterministic side of this topic. We also developed a random quenched side, still in progress, of this topic. And in particular, we speak about it in 2 days on the other place, still in Pisa. Okay, so today I will speak about the deterministic side of this argument. In particular, this deterministic side was more or less completely done in the first 2 papers with my collaborator Nikolai Haidin, who is here, in particular exploiting very beautiful ideas by Nikolai about recurrence properties in dynamical system. And the last 2 papers just concern, still in progress, concern the random aspect of the same topic, but I will skip it, because today what I want to do is to present a new get the same kind of result. I will show you in a moment what the results are, using a spectral approach. And in particular, the spectral approach will be helpful either for the deterministic situation, which I'm going to present today, and the random situation. By the way, it will be the subject of the last 2 papers. Okay, so now let me briefly put the problem. The problem is very easy. Okay, sorry, I think I forgot one. Okay, there are 2 questions, very simple question in dynamical system. So suppose you have a set U in some phase space, and of small measure, it will be called rare events, and then you ask the following question: what is the probability larger than n. Now, if the target set is chosen with the normalization that this probability asymptotically goes to the exponential 1 is e minus theta t. It is a number between, and this is called the Gamble law or extreme value law. But in this case, I didn't speak about extreme value. Simply, I spoke about the statistic of the first degree. I don't want to speak about extreme values. And now let's go to the second question, which is the main topic. Okay. Okay, here. No, come back.
Come back. Okay.
Okay. Okay, the second question is just the main topic is the following one. No, exactly this one. Okay, now we look at the second question, which is the following. My orbit, my state enters the set UN, which is a sequence backed, by the way, of sets. And I look at the occupation time of this set, which is given by equation 3. And I look at the probability that the number of times my state stay into the set U is equal to K, right? So this is, okay, this is some example here, but now I skip it because we are late. So the question is, can we give an answer to the asymptotic distribution for when the size of the set, which is n in our case, goes to infinity, so the set goes to 0? This is the question. Okay, what we expect is this gives rise to a Poisson distribution. But you will see the answer is a little bit more complicated. It's not really a Poisson distribution, but it is what is called compound Poisson distribution. So now I need to briefly record what is a compound Poisson distribution. Look, an integer value, a random variable, is called W, is called compound Poisson. If you can write it as the sum of IID random variable with distribution lambda L up to a certain variable P, which is distributed according to the standard Poisson distribution. This is the usual definition of compound Poisson distribution. Here we have two examples which will play some role in my talk. The first is the standard Poisson, where there is only one variable distributed exactly according to the Poisson distribution. And the second one, which is pretty interesting, is called the polyhyper distribution, for which you have this distribution for the mass distribution of the random variable itself. It will play a role later on. Another way, which is exactly what I'm going to use, is another characterization of this kind of compound Poisson in terms of characteristic function. In particular, first of all, you have to introduce the notion everyone knows more or less what is the infinite divisible distribution, a distribution which can be represented as a sum of n IID random variable defined on the same space. In particular, there is another way to characterize the infinite divisible distribution in terms of characteristic function. So the characteristic function phi of t of an infinite divisible distribution may be represented at the power of other characteristic function. This is exactly what I'm going to use now in order to characterize what we want. So this is an example of this kind of compound Poisson distribution. Since it is also important to speak about application here, in particular to climate, this is taken from a work which I did with some physicists, where we applied this idea of recurrence or extreme value or Poisson statistics to climate data. And here we look at the distribution of an observable in the neighborhood, a small neighborhood of a fixed value of some observable, in particular observable was the sea level pressure, with real data. It's not maps or simulation using tool example. This is a real data, and it's pretty astonishing that with this data we can fit one kind of this compound distribution. So the blue one, the red one is one of this compound Poisson distribution, which we try to fit with the real data, and it's amazing that we can fit it with real data. Okay, now I will present a okay, now I will present the new technique in order to get this in a very simple way. First of all, we can apply it when we have some operator which evolves measure or density. This operator can be either operator in dynamical system, which we call transfer operator, pair of opinions operator, or it could be the Markov operator if we have a stochastic differential equation. So it's very broad range where we can apply this idea. And in fact, in a paper which we are writing with Franco, Stefano, and Paolo, we are just applying this idea to stochastic differential equation because we have the Markov operator which fits with the assumption which I'm going to give you. Okay, so we have to compute the distribution of these random variables, and in particular the n which is given here, as I said before, it must be taken related to n. So this is what we call case scaling, but okay, it's a scaling which allows us to do what we want to do. And then what we do is we take the characteristic function of this object here. In particular, k, now I put k generic, but it will be n in our case. So the idea is very simple. Okay, we want to show that the characteristic function of this object here will converge to a compound Poisson distribution. And we have done. So it's very simple. The point is that since we are working with operators, first of all, our operator, whatever it is, applied to a function f, we modify it in this way. We have the operator now is applied to an observable f in some Banach space, times this exponential factor, where hn is exactly, in this case, I'm sorry, I called it un before, but it's exactly our real set, our small sets. And now, since the operator has some property of duality, it is easy to see that the k power of this operator is exactly equal to the unperturbed operator to the same power k. And so, what is important to know is, okay, if you never work with this kind of stuff, let me tell you that are very general. They can really be applied to several operators. What is important is this equation here, because here the characteristic function we are computing, which is pegged to some stationary measure, because this operator move the measure in order to get the stationary measure at the end. This is the stationary measure with some density here, can be written in this way. So basically, the characteristic function now became this integral here. So now the idea is very simple. Okay, we have this operator here. Okay, if we can find an eigenvalue of this operator, which is a perturbed operator, which is pegged to the previous one, and if we can relate the eigenvalue of this operator, which we don't know, but if we can relate to the eigenvalue, the maximal eigenvalue, or unique maximal eigenvalue of the unperturbed operator, we have done, because we can do this integral here. That is exactly what we can do. Of course, in order to do it, we have to use some spectral result. In particular, here we use a spectral theorem by Kelly-Liberan, which was proved in the context of dynamical system. But the previous result is we can apply it to a very general operator. So lambda ns is the operator of the perturbed of the eigenvalue of the perturbed operator, the unique maximal eigenvalue, and one is the maximal eigenvalue of the unperturbed operator, and the two are related by this equation. Of course, there's some work to get it. It is just the content of this perturbation theorem. And what is interesting is theta s is exactly given by this expression, and these terms here are terms which are in principle computable on example and in practice, because they tell us very simple fact. We are in some set un, which is our original small set. Then after k plus 1 time, we come back in this original set, and then it adds. So basically, this quantity here can be computed, and there will be computed. So if I have this quantity here, we can construct this term, provided this sum converge, but this is just an assumption which must be verified on concrete examples. Then we can find this expansion of the maximal eigenvalue, and then we put into we work on this, but this is equal to this, and then we get the characteristic function. Now, this characteristic function is a real characteristic function because it's continuous in zero. And moreover, it's very easy to see, probably in the next slide, that is infinitely divisible because if you divide the t by n and you take the n power, we get the same result. So by moreover, since these are discrete random variable, positive discrete random variable, they will converge to discrete positive random variable. Moreover, the asymptotic law is infinitely divisible. So by a theorem by Feller, it means the limiting value is a compound Poisson. So we only get with this technique, provided theta s is continuous in zero, and it is, we get surely that what we are looking for are compound Poisson thanks to this theorem by Feller. And okay, so this is exactly what I was saying. This is the proof that this distribution is infinitely divisible, is trivial. This provided, and the fact that the value are the value are integer, the random variable before going to the limit are integer value. So the limiting value is also integer value implies that the limiting in distribution random variable is compound Poisson. But we have the characteristic function. But now, by leaving inversion formula, we can get also the mass distribution. So the distribution of the variable, which is the formula. Everyone working with this formula knows it is very difficult to get this integral unless we have something here. But let me present you two examples which were also obtained in previous techniques. Here it's very simple to get this. Okay, the first example is a point which is not periodic, and we have set shrinking around this point. So all the quantity Q, which I showed you before, you are in some set, you come back in the meanwhile, you can escape n times, can be computed very easily by using some consideration, continuity, and so on and so forth. And you get immediately the characteristic function. This is example, the first example. And okay, so written there, the characteristic function is Z1. And if you look on probability book, this is exactly the characteristic function of a standard Poisson. It's very simple. A little bit more complicated example is when you have a periodic point. Well, in this case, see the periodic points attracts points close to it. We cannot talk to have, okay, we have some stacking, some clusterization around this point. The computation can be done, and this is exactly computation in the paper. You can compute all this quantity Q. And so what we get at the end is this characteristic function. Well, so you open again the book, and you see that this characteristic function is exactly the characteristic function of this distribution, which is called polyhedric, which is a very famous compound Poisson distribution. Okay, now, yeah, and then you can generate a lot of other characteristic functions, but the point is, if the characteristic functions are different from these two, it's very difficult to get the mass distribution. It's very difficult. We have mixture of characteristic functions, and you don't see exactly what these are. But you see, this is interesting for people working in climate because usually in climate, people are looking for what they call the extremal index, which is one parameter giving you some information about are the clusters forms for orbit which are stuck around some point. Here we get further, so we have a higher order statistic about it, and this is something which we planned to study even with physicists. It's something which I really planning to do. Just to tell you that all this theory can be developed in the quenched setting. It's a little bit more complicated, using either this technique or what I did with Nikolai, other techniques. And the other techniques, in some sense, are much more powerful because we are not. I mean, we can go beyond the spectral approach. It requires a lot of degree of mixing. Okay, thank you very much for your attention.